Science Club. We are comprised of about 8 members right now, so it's one of the largest groups we've had in quite a bit. My name's Adam Larson. I'm the president of the engineering club. This is Gabriel Garcia. He's our vice president, and then Shane Ellison. He's just one of our members. So last semester we designed and built a catapult. So you want to take over the planning process here?
Yeah. I remember when this idea was proposed, Adam and I were walking back from Dynamics after class. We were walking to our trucks, and I was like, you know what would be kind of cool? If we built something to throw pumpkins for Halloween. And that's when the idea was born. We proposed it at one of our meetings, and then we started talking about it. So the first thing we had to decide was between a trebuchet or a catapult, because trebuchets tend to be more powerful, but they also are a lot less predictable. So that's why we went for a catapult, because we didn't want it to fling a pumpkin straight back at us. So that's why we decided to do that. And then I started using AutoCAD to draw up a basic design, and we went through some maths, which you're going to cover a little later, to come up with our goals, because we wanted to throw a pumpkin 300 feet. Then we had to go about dealing with SGA and getting a budget and whatnot, and getting that approved, and then buying our materials. And one of the bigger challenges was figuring out what to use for the actual arm, because we needed something that was light enough to actually be, moved quickly, but still strong enough to withstand getting smacked into a couple of 2x4s every time. So one of our previous members, who is now at UW, we miss him dearly, found us a stop sign pole. We didn't question where he got it. So he just said, hey, we got this stop sign pole. I was like, okay. So if your neighborhood's missing a stop sign pole, that might be why. We cut it down to size and built an arm out of it. And we got some pillow bearings and ordered a metal rod through the college and put it all together and did some designing and testing, and it was ready by that week before Halloween.
So overall, we got this project done in a reasonable timeline, I would say. We started October 6th with just purchasing all of the materials that we would need to build the catapult. October 13th, we had the main frame built, so we had everything assembled, everything ready to go. We still hadn't had the arm on it, and we needed to determine the length of the arm. The 23rd of October, we tested it and determined our analysis off of it, although we'll talk about it didn't go as far as we wanted the pumpkins to go later on. And then October 27th, we displayed it to everyone, and then October 31st is when we did the final display and launched the pumpkins for everyone.
So, this is just our sort of materials list. We had to definitely go back to the drawing board a few times for this design. We went to Home Depot many times. You never go to Home Depot once. And one of the biggest challenges that ended up coming was from this rope. We originally wanted to have like the pin set up to where you had like 2 eye hooks, and then the hook to the arm, and then the pin through it. And then we wanted a rope on the end of it that you would just pull the pin. Turned out that when you have about 600 pounds pulling on it, it's hard to pull a pin. And the rope kept breaking. So we ended up just grabbing a chain from my truck and then attaching it, just whipping it out. And that's what we ended up having to do. And then we used the rope we bought as sort of a safety pin, because we had it set up to where we had this safety pin that you would pull from a distance, and then this had the chain on it, and you'd yank. And this used to be a uniform shape. As you can see, it no longer is. That's how much forces we were dealing with. Then we used the mixing bowl for our actual basket. The first one we had was a little bit too small, so the pumpkins wouldn't actually sit in it, they would sit on top. And so when we launched, the force of that acceleration just crushed the bowl. So we had to get a bigger one. I don't know if the videos are on this. I know Sarah was there when it happened. She recorded it, yeah. Yeah, and we had casters. This was one of them. One of the problems we ended up having was during the launches, the back end of the catapult would also go up because the arm would smack into the top board and it would bounce. And so our solution to that was we just found a big boulder and heaved it onto the back. But the problem was that it would still bounce a little bit, and it ended up destroying our casters. Both of the rear swivel casters like exploded and sent ball bearings everywhere during the final test. And so we had to wheelbarrow the whole thing back. Oh, here's some of our pictures.
Yeah, so construction phases, like Shane talked about a little bit earlier. We first started off building that base, getting a understanding of how long and how wide it had to be. We decided that it had to be super wide because none of our forces are going to be acting in this way. They're all going to be acting this way. We also added on these reinforcements to the sides. Up here you see Jose, and then we have like 4 2x4s up there, and they're all reinforced into these AA frames. And even then, those were splintering by the end of our testing. We even put padding, and still they're still getting chewed up. So it was a lot of fun to see that happen. And then we finally attached the arm. Here you can see Steven, our advisor, helping Jose put in our metal rod that we had to order for our pivot point. And then our elastics, which caused us most of the issues with deciding how we're going to launch it. We ended up going with our elastics like this, and we were attaching them to like a gate handle, and that would be looped through and up to 2 other like handles up here on these those 4 2x4s. So we went ahead and did that, and even as we were cranking it back with our come along, the entire thing would just be creaking the entire time. And we'll see our point of failure here when we look at the math behind all of this. So
yeah,
we'll look forward to that.
One of the main reasons it didn't launch as far as we did is because we were too scared to pull it all the way back. Because it would start making scary noises. We're like, we don't want this to explode.
All right. Well, some of the engineer aspects that we took upon doing this project, some of the outcomes. Our throwing distances weren't necessarily what we calculated them to be when we did the calculations. We got about 100 feet from small projectiles, and then 50 to 70 feet on the large projectiles. The smaller projectiles were smaller pumpkins that we launched, and then the large projectiles were normal-sized pumpkins that we launched. Another engineering aspect that we used in this project was our budget. We had a budget of $600, and we spent $400. That's a main aspect, saving money while building what you're supposed to build is huge. Some of the design aspects we used in it were CAD, SolidWorks, and then also hand-modeled drawings. The negatives that we had upon this were, like Gabe or Adam talked about, the wheels, they exploded, they came off the thing. We also had a slight bend in our bottom of our frame from the forces that were put onto the bottom part of it. And then the elastics part, like Adam was talking about, we also had big troubles with. And then, of course, it required multiple people to move it instead of just one person.
Alrighty, so here are some of the videos. The quality isn't the best, but those are our small ones. And then here's a larger one.
Alright guys, we need to do a countdown. You want any more bacon? Alright, ready? 3, 2, 1, stand behind. Stand behind.
Yeah, so that was a lot of fun to actually go out with the Intro to Engineering course. They built their own smaller versions of a Catapult, and one group even did a trebuchet. It was awesome to see how their designs worked out as well. So we got to see a lot of good pumpkin throwing that day. Alrighty, so for these calculations, we looked at 2D motion to determine how far we had to go with our pumpkin. So we wanted to shoot for about 300 feet. We just decided that because we went out to Google Maps, like measured the baseball diamond out there to see how far we could go. We didn't want to hit the hospital or hit someone on the running track. That was one of our main concerns. That would not, it would be funny in the long run, but also,
Yeah, running on the track and then getting hit by a pumpkin.
yeah, yeah. Then we also had to look at torque and inertia and rotational kinematics. So once we determined the acceleration we need the pumpkin to go at the very start, once it leaves the basket, we had to determine how fast does this arm have to be moving in order to accelerate up to that point. And then taking that acceleration, we were able to determine how much force we would have to put on this arm to cause the weight of the arm and the pumpkin to move. So it was a lot of fun seeing all those play out since we've been going over those for the past 3 semesters, and now that we're in mechanics of materials now, we kind of have a better understanding of why our frame is acting like that. So I have a couple of demonstrations we're going to look at. So let's see, a marker. My favorite, using the whiteboard. If you ever come by the engineering lab, where 90% of our work is up on the whiteboard before we put it down on paper, so we have a lot of fun. So what we were primarily using was 2x4s for our main base components. And usually, we'll see in the math here shortly that this direction, it doesn't bend quite as easy as bending in this direction. Right? So we had our pieces built like this and this to make this square. So to determine that, we look at our square. And Gabe has my tape measure here.
Yeah.
So we'll look at the dimensions really
You
quick.
can see the frame
Just
up
in
there.
this case. So we have a 1 inch by, I'm just going to say 3.5. I'll just round to 4. Just for simplicity's sake. Engineers, we just like simplify, it's nothing to be too concerned about. So if we're bending about this x-axis versus the y-axis, so this is our x-axis where we would be bending across. We have our moment of inertia in the x direction, and that equation is 1/12 base times height cubed. And in the y direction, if we are bending, we're going to have Iy equals 1/12 base cubed times height. Those pretty much, the difference between these is how you're looking at it. So instead of looking at here, we look at here. So it's not too hard to figure out. So by doing this, I'll pull out my handy dandy pocket calculator. We get, let's see.
Don't mess up, man.
Dang. Okay. 1/4. Let's see. To the 3rd power all over 12. Let's convert that. Let's see. I'm sorry. Where? That's it. So we get about 5.33 inches to the 4th power. The base has 1 power and then 3 here. So if we look there versus if we do this, 1 cubed by 4, that's just going to be 4 in the numerator. So
So just 1/9.
yeah, 1/3, which is Yeah, 1/3. 0.33, sorry. 0.33 inches to the forward. So we see that as our moment of inertia is greater, that's when our material can bend easier. So if we were to look at our PVC here, what do we realize about this if we're looking at just the cross-sectional area? Well, we see that the diameter, it's symmetric, right? It's symmetric all the way around. So we don't have to look at the X or Y component, but we can see that it still bends a little. I'll pass these around. I guess this, and we'll do this one.
Wood.
Yeah, wood. This isn't quite as symmetric, and it's going to be harder. This one's a little easier. That one's going to not bend as much.
I bet Chuck's gonna break it.
Yeah, Chuck might break it.
It'd be amazing if we just like.
So now we look at the PVC that I've passed around, and we're just going to assume that it's going to be solid all the way through. And I think when I measured it in the classroom, it was 1 inch in diameter. So looking at that equation, we have I equals 1/4 pi r to the 4th. So when we plug that in, you get 1/4 times pi times 0.5 to the 4th power, and we get 0.049. So we see that it's a little easier to bend than this, but it also depends on the material that we're using. And then our final example is a common I-beam. Okay? These are usually made of metal, and we could have made our catapult out of metal. It would have been stronger. It would have been, it probably wouldn't have bent as much as the wood does. But also we have to keep in mind, like Shane said earlier, of the cost efficiency. So when we look at this, and this is where I always get the Steven smiley face on my exams, for the, not the units, not the units, it's including, well, okay, Steven, all right, so if we look at this I-beam, right? All right, so when we look at this, I have the measurements here. I did it a little bit earlier. So those plastic ones here, we have 1.5 inches here, 0.25 here, 0.25 here, and 1.5 here. So when we're looking at this, this is a composite shape. So we can look at this as if we were looking at 3 separate rectangles. So we're going to look at this similarly, and we can use this bending of the x-axis. I'm not going to look at the y-axis. When you look at it, when you get a hold of it, if you bend it where you have the I-beams between your finger, it's going to be tough to move. But if you rotate it 90 degrees, it's going to be easier to bend. Yeah, just like that.
Twist it a lot easier too.
So we follow this equation. I'm going to call this shape 1, 2, and 3. So we can look at the sum of the moment of inertias. We can look at I1 plus I2 plus I3. So when we look at that, we get 1/12. I'm just going to simplify this to 1.5 times 0.25 cubed plus, that's 0.25 times 1.5 cubed plus 1.5 times 0.25 cubed. And now this is where I usually get my points docked off. So this is our centroid line. Since the centroid of this and the centroid of this is not coincident with this line, we need to account for that distance. So we look at D1 and D3. So we also need to include our plus AD squared. So that's going to be, let's see, that's going to be 1.5 times 0.25. You want to start plugging this into a calculator? It's going to be a minute.
You're gonna make me use a TI.
Yeah, I'm sorry. So 0.25.
I'm a Casio Master Race.
So that's 0.125. Here. 0.125 plus this 0.75 here. And these D's are going to be the same because of symmetry, and then we're going to end up with 0.875 there squared. And then we're going to have two of those because we have to count for both the top and bottom.
Give me a minute.
Yeah. So what we'll realize is that this is going to be much greater than this. But so back to the most economical way that we can see this. So buying metal isn't always the most effective thing because you're going to have to look at different stresses. Sometimes this is just too much. Sometimes the material, they don't make it in that specified material in those dimensions. So our next best bet is to look at like a house truss beam. This is like either in the floorboards or up in your attic. And so they'll just create this by themselves just by notching this out and gluing it in together to make it a composite material. And yeah. So we're just gonna pretend that didn't happen, and yeah. So that is what we should be seeing. Yeah. Alrighty. Well, thank you. Yeah, so we're in the room 1441, so if you just ever want to stop by, say hi. That's where you can see us. We're also working on an off-road wheelchair, and we were going to talk about that this semester, but
It's not done.
yeah, we just got our materials yesterday, so we're going to hopefully get that done by the end of semester, and
If
we'll go
not,
from there.
We'll go to the next club like it's been going to for 6 years.
yeah, so we'll hopefully have that done this semester. Yeah, thanks again. We appreciate it.
Good job, you guys.